we will study some application. So this is called variational inequalities. Suppose you want to solve the system of linear equations Ax equal to b. This is the same as saying y transpose Ax equals y transpose b for all y in Rn. So you can write it in this form also. So we treat x as a column vector, b is a column vector, so y transpose is a row vector, and so this is the inner product. So generalization of this to higher infinite dimensional spaces is to have a bilinear form, let's say in a Hilbert space, and to solve Axy equals Fy for all y in H. Okay, H is a Hilbert space and you want to find an x in H, so find x, and this is a bilinear form. Variational inequalities are further generalizations of this, and they occur especially in constrained optimization problems. That is why the name variational comes there. And many problems in science and engineering can be put in this form, like two-phase heat transmission problems like melting of ice or the stretching of an elastic membrane over an obstacle, etc. They can all be cast in the language of variational inequalities. So today we will study an important existence theorem for variational inequalities. Okay. So H is a Hilbert space, and you have A from H cross H to R. So we will deal with a real Hilbert space this time, okay, because we are going to do inequalities. You can't do that in complex numbers, and anyway you have to go to the real part, and therefore you might as well deal with the real Hilbert. So A H to R is a bilinear form. That means you fix one variable, then it is linear in the other variable. That's what we have, a bilinear. A typical is the inner product in the real Hilbert space is a bilinear form. Okay, so and this is continuous if there exists an M positive such that for every xy in H we have mod of Axy is less than or equal to M times norm x norm y, and then it is called H elliptic. Another word is coercive. This terminology we have seen before, and you will know immediately why I am having that. If there exists alpha positive such that for every x in H we have Axx is greater or equal to alpha times norm x square. Okay, so then it's called H elliptic. Okay, so example, inner product is a continuous H elliptic bilinear form. It's bilinear and then it's continuous by the Cauchy-Schwarz inequality, and H elliptic, in fact xx gives you norm x squared itself, so alpha equals 1. More generally, if you have A is a symmetric continuous and H elliptic bilinear form. So symmetry means what? Axy equals Ayx for all xy in H. Then you can define xy, a new inner product A. So this we can define as Axy. Well, it's linear in both variables, it is symmetric is given, and Axx is greater than or equal to alpha xx. So norm A norm x a is the square root of axx. So this gives you a norm, and in fact this norm is equivalent to the original norm, because norm x a square is less than or equal to is equal to a xx, that's less than or equal to m times norm x square by the continuity, and greater than or equal to alpha times norm x square. And therefore you have norm x a is equivalent to norm a. So you get an equivalent inner norm and you have a new inner product. Another example, so if you have Rn with norm 2, so that is our space Ln2, and A is a n by n matrix with real entries, real, and then you have AXY is Y transpose AX. So this is a bilinear form and obviously continuous. So if A is positive definite, then AXY is elliptic, Rn elliptic or Ln2 elliptic, whatever you want to say. Okay, so now let us prove the main theorem in this connection. So theorem, and this is due to Stampacchia. So H real Hilbert space and A from H cross H to R is a continuous and H elliptic bilinear form. Let K in H be a closed convex subset, and finally let F belong to H. Then there exists a unique U in K such that, let's say X in K such that A of X Y minus X is less than is greater than or equal to F of Y minus X for all Y in K. A of X Y minus X greater than F of Y minus X for all Y in K. So these are called variational inequalities. Okay, so we are proving an existence theorem for this. So instead of AXY equals F, which we had here, we are now having an inequality instead, and these, as I told you, are connected to constrained optimization problems, especially if A is symmetric, and therefore we have it's interesting to prove the existence theorem. Okay, so proof. Let U in H be fixed. Okay, then V going to AUV is a continuous linear functional. Okay, because of the continuity of the bilinear form. Therefore, by the Riesz representation theorem, there exists a AU in H such that AUV equals A of UV. I should have usually put it in the second coordinate, but now we are in the real Hilbert space, so I'll be fairly carefree in the sense that it is symmetric, and therefore I can put it anywhere here. This is for every V in H. So by the representation theorem. So clearly, so mod AUV is less than or equal to M times norm U norm V, and therefore you have that and U going to AU is linear, and norm of AU is therefore less than or equal to M times norm U. So A is belong to L of H, okay, and you have AUU equal to AUU greater or equal to alpha times norm U square. Okay. So let me call this variational inequality as star. That's the problem which we have to show. So star is the same as saying find x in K such that Ax y minus x is greater or equal to f times y minus x. Okay, which is equivalent to saying find x in K such that you have minus rho Ax plus f y rho f y minus x is less than or equal to 0 for all y in K. Where rho is strictly positive. And I can therefore write this also saying find x in K such that minus rho Ax plus rho f plus x minus x comma y minus x is less than or equal to 0 for all y in K. Now this looks very familiar. So this is something minus x, y minus x is less than or equal to 0. Okay, so this is like the projection inequality which we proved, and therefore we are saying, so this says the projection of this vector with respect to K is in fact x. Okay, x minus pkx, y minus pkx is less than or equal to 0. That was the kind of thing. So we have here, so that is equivalent to saying you have x equal to pk of minus rho Ax plus rho f minus x. Let us call this as, so we will define this as Sx. Okay, so we are having a map S from K to K. Okay, x is in K, and then I'm defining pk of it, so it comes back to K, and I want to find a fixed point. So that is find a fixed point of S. And so now let us look at this. So norm of Sx1 minus Sx2 is equal to norm of pk minus rho Ax1 plus rho f minus x1 minus pk of minus rho Ax2 plus rho f minus x2. So this is plus x here, sorry, there was a plus x, and therefore you have plus x1 plus x2. Okay. And that we know pk of x minus pk of y is less than norm of x minus y. We have shown this, and therefore this will give you norm of x1 minus x2 minus rho of ax1 minus x2. Rho f will get cancelled. Okay. So now we square this and develop it. So now sx1 minus sx2 square is therefore less than or equal to norm of x1 minus x2 square minus 2 rho a of x1 minus x2 x1 minus x2 plus rho square norm a of x1 minus x2 square. Now let us write this whole thing as I am going to write it as norm of x1 minus x2 square. So for the first term I will get 1. Now ax1 minus azz is greater than alpha norm z square. There is a minus sign here. So minus 2 rho alpha times norm x1 minus x2 square plus rho square, and then a norm of ax is less than m times norm x. So this is again m square. Okay. So this is less than this. Now I choose rho. I haven't chosen rho yet, so I am now going to choose a rho. So choose rho such that 1 minus 2 rho alpha plus rho square m square is strictly less than 1. That means, that is, rho is less than 2 alpha by m square. That is 0 less than rho. So choose rho such that this. Then this thing is, so this will imply this number here is strictly less than 1. So this implies sx1 minus sx2 is strictly less than some alpha beta times norm x1 minus x2, where beta equals 1 minus 2 rho alpha plus rho square m square, and that has been chosen to be strictly less than 1. Okay, so then this contraction implies there exists a unique fixed point, and therefore that proves the theorem of Stumpaki. Okay, so we have found a unique fixed point of S, and that is precisely the solution of the variational inequality. So corollary, this is called the Lax-Milgram lemma. Okay. So H Hilbert and A H cross H to R continuous and H elliptic. Okay. F in H is given, then there exists a unique x in H such that AXY equal to FY for every y in H. So this is exactly the solving infinite dimensional version of solving n linear equations in n unknowns, which I started in this lecture with. Okay, so proof. So K is now equal to H. Okay, so this is we can apply the Stumpaki's theorem. So there exists a unique x such that ax y minus x is greater or equal to f y minus x. Okay, so now take any z in H. So you write y equals z plus x. This is also in H. So then you get AXZ greater than or equal to FZ for all Z in H. Now you apply it for minus Z, then you will get the opposite inequality. You will get less than or equal to, and therefore AXZ equals FZ for every Z in H, and that proves the Lax-Milgram lemma. Okay, so the Lax-Milgram lemma is the, as I said, the infinite dimensional. So remark, infinite, so Lax-Milgram lemma can be thought of as the infinite dimensional generalization of the fact that a positive definite matrix is invertible. If you have a positive definite matrix, it's invertible, it's deterministically positive, and you have you can uniquely solve Ax equal to B, and this is exactly the generalization. And positive definite matrix is Axx, x transpose Ax is greater than alpha norm x square, and therefore you will get precisely the generalization of this. Okay, and this is the cornerstone of the existence theory for elliptic partial differential equations, and it's also for numerical methods like the finite element method. The Lax-Milgram lemma is in fact a very useful tool. Okay, and in the symmetric case, A is symmetric, then X can be thought of as the minimizer. So X in K minimizes 1/2 of A xx or Ayy minus Fy over K. Okay, so this functional, so J of y equal to this is so J of x equal to minimum of Jy y in K. Okay, if A is symmetric, you can interpret the variational inequality as this, and the variational inequality becomes the equality, namely the Euler-Lagrange equations, when you have this, it is the whole space, and therefore that is the Lax-Milgram lemma. Then Lax-Milgram lemma also, so Lax-Milgram also holds for any closed subspace. That means if W contained in H is a closed subspace and A is continuous and elliptic, continuous and H elliptic, and then F is in H, then there exists a unique W in W such that AWB equals FV for every B in W. Okay, so this it can also be very easy to prove. Just again, it's the same, exactly the same proof which I used for the Lax-Milgram lemma, and therefore this can be. Okay.